going to work through an example of a particle that has a given trajectory. So the position of the particle is a function of time. It goes as a quadratic term, ct squared, and then a cubic term, minus bt cubed. And these are the questions we're going to try to address for this function, sort of as a way of practicing some of the things we'll need from calculus. So first off, dimensional analysis, always a good idea. What are going to be units of measure for both c and b? When does x reach its maximum value? So find an extrema of a function. Applying the function, so what is the displacement of the particle between times t equals 0 and t equals 4 seconds? So we'll just evaluate the function at those two times. And then use of the derivative. We want to know the velocity of the particle at a specific time at 3 seconds and the acceleration of the particle at a specific time of 3 seconds. All right, so for the first question, what are the units of c and b? Well, if we write out our function, x is a function of t, is ct squared minus bt cubed. Each of these individual terms needs to be length in meters. So I know that this is a meter, and to have equality, this combination ct squared has to be a meter, and then to subtract bt cubed from ct squared, they have to have the same units, or else you can't add or subtract them. So bt cubed also has to evaluate to be a meter. That means c times time in seconds squared is a meter. So c is going to have units of meters per second squared, which means it is an acceleration. And then b times t in seconds cubed is a meter. So b is going to have units of meters per second cubed. So b doesn't come up very often, but just go ahead and tell you what the name of that is. That is a jerk. Higher order derivatives of position with respect to time have fun names like snap, crackle, and pop. Those things don't come up. They don't have like forces depend on those higher order derivatives of position with respect to time, but it can be fun. And if you happen to go into roller coaster design, that is an example where like an exciting roller coaster ride is not just an acceleration, but a change in the acceleration. So jerk and those higher order derivatives are important in quantifying a good ride. All right. To answer the questions 2 through 5, I'm going to put specific values in now. So now I change to say, let's let x is a function of time be 3t squared minus 2t cubed, just to have specific values so we can answer things. All right, and then we want to answer the question for 2. Where does x reach its maximum value? So if I imagine I have some function of time, not necessarily this one, and it does something, say like that. And we want to think about extrema for that function. Well, if I follow along on my function, it keeps getting bigger, gets bigger, gets bigger, gets bigger. Then I reach a point where the slope goes to 0, and it's as big as it gets, and then the slope turns back over and I have a negative slope. So now it gets smaller, 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 smaller. It's as small as it can get. It starts getting larger again. So the nature of finding extrema is I'm looking for points where the slope goes to 0. That's telling me as this parameter of the function changes, the function is no longer getting bigger, it's no longer getting smaller, the slope vanishes. Therefore, I'm at an extrema. So when we want to find an extrema for this function x as a function of t, what we're looking for are the points where the rate of change of x with respect to time, which is velocity, vanishes, goes to 0. All right, so now it's a little exercise to do that as we have our function. So dx by dt is d by dt of 3t squared minus 2t cubed. Just go through this in all its glory. So I can pull the d by dt in, and it's going to operate on this term and on that term equally. So I will have a d by dt of 3t squared minus d by dt of 2t cubed. I can pull the constant through the derivative. So this is going to give me 3 d by dt of t squared. This is going to give me a minus 2 d by dt of t cubed. All right, the derivative of t squared with respect to t is 2t. So this is going to give me a 3 times 2t. I have a minus 2, and then d by dt of t cubed. The d by dt of t cubed is going to give me a 3t squared. So I have a minus 2 times 3 times t squared. If I factor this, I'm going to have a 6 times a t in the first term minus 6t squared. And we can simplify that a little bit. I'm going to write this out as dx dt equals, we will have a 6t times 1 minus t, and we are asking where does that equal to 0? And that's clearly going to have 2 zeros. We'll have a 0 at t equals 0 and 1 at t equals 1. So we have the when, and then if we wanted a where do those zeros occur? Then we just go back to evaluate our function. X when t equals 0, and our function was 3t squared minus 2t cubed. So x when t equals 0 equals 0. And then the where when time equals 1 second. 3t squared is going to give me a 3, and minus 2t cubed for t equals 1 is going to give me minus 2. So it's 3 minus 2, otherwise known as 1. Out of those two, x max is going to be 1 meter, because that's the larger of the two extrema that we found. All right. If you are taking calculus at the same time as this class, or you're feeling rusty on calculus, we have a very much a hands-on approach to calculus as regards physics. It is a tool to be used. In the appendix of your book, there is literally like a single page out of that lists the derivatives and the integrals that we'll need over the course of this semester. And you're not really concerned about the derivation of mathematical truth. We are very much about applying mathematics. All right, our third question. So the displacement of the particle between t equals 0 and t equals 4. Let me go ahead and write down our happy little function again. X as a function of time is 3t squared minus 2t cubed. We want to evaluate that to get the displacement. So delta x, the displacement, is x when t equals 4 minus x when t equals 0. We actually just found that, and we found it to be 0, so I can go ahead and throw that out. So our displacement is x when t equals 4, which is going to be 3 times 16 minus 2 times 64. So that is 48 minus 128. So delta x, the displacement, be minus 80, and I'll put in the meters. And this displacement is negative. That's completely fine. You need to keep track of signs. You don't want to drop them or put them in inadvertently, but it's completely fine for the displacement to be negative. It just means that this particle has wound up further to the left than it started at. All right, fourth question. I'm going to find the velocity of the particle when t is equal to 3 seconds. Okay, so our notation, v when t equals 3, means we want the derivative of the function of position with respect to time, and we're evaluating that function at 3. Okay. So the derivative of position with respect to time, this is going to give us our 6t. And this is going to give us a minus 6t squared, and we're evaluating that function at t equals to 3. So just go ahead and do that. So that is 6 times 3 minus 6 times 9. So I've got a 18 and a minus 54. So the velocity at t equal to 3 seconds is going to be minus 36 meters per second. All right, and then the last thing we were asked to find is what is the acceleration then at the time t equals 3. So let's go ahead and do that last bit. So fifth question, the acceleration at t equals to 3 is taking the second derivative of position with respect to time, which is the first derivative of the velocity with respect to time. And so that is d by dt, and the velocity we had was 6t minus 6t squared. And so we evaluate those two derivatives, and then set time equal to 3 seconds. So the acceleration at t equals to 3. I've got the first derivative of 6t is going to give me a 6, and the first derivative of minus 6t squared is going to give me a minus 12t. I'm evaluating this at 3. And so this is going to give me 6 minus 36 minus 30 meters per second squared. Alrighty. I might recommend as a good little bit of practice if we go all the way back to our starting function, instead of just evaluating individual points. You probably have a graphing calculator, or can use an online web service or Wolfram Alpha or whatever is your favorite to plot this function and see what it looks like. The 3t squared minus 2t cubed, not that complicated a function. We also found velocity as a function of time, plot that. We also have acceleration as a function of time, plot that, and see that those functions make sense to you. That when the position is increasing with respect to time, has a positive slope, has a positive velocity. Where the position is a function of time, where the slope goes to 0 is where the velocity is going to vanish. And it's either going to go from being a positive velocity to a negative velocity, or a negative velocity to a positive velocity. So go ahead, plot for yourself the position as a function of time, its first derivative, and then plot its second derivative, and see that those functions make sense to you.